Okay, welcome back. We're going to continue on with lecture 5 here. And what I want to talk about are next are Bronsted acids and bases. And so these are a subset of Lewis acids and bases. So, and this is these are what we're going to spend most of the semester. This is most common for what we'll be discussing. So very simple. Bronsted acid is something that can donate a proton. And a base is something that can accept a proton. Okay. And so an example of this would be acetic acid and ammonia. So. Okay, so the species all the way on the left is acetic acid. This is found in vinegar. That's what gives vinegar its sort of distinctive smell. Ammonia, of course. And on the right, we have acetate ion and ammonium. Ion, okay. And so as we did with the Lewis acids and bases, we can use the arrow nomenclature to describe the flow of electrons. So I start with my electrons on nitrogen, have them attack the hydrogen on acetic acid, and then I need to break that OH bond. The electrons in that bond are going to leave with the oxygen. So I push them onto oxygen, and then that gets me to my products. Okay. You also note my charges are matched. So I've got net zero charge in the starting materials, net zero charge in the products. So I'm okay there. And what I want to do is introduce this idea of what we call conjugate acids and bases, okay? Or conjugate relationships. Okay. And so what we say is that acetate ion is the conjugate base of acetic acid. Okay. And we can say that ammonium ion is the conjugate acid of ammonia. Okay. And so basically the term conjugate allows me to, very concisely relate one species to another. So, I can say deprotonation of, this ketone to make its conjugate base. Everyone knows what that means. Or protonation of this anion to form its conjugate acid. Okay, it just gives us a nice, easy way to to tie together two compounds that are related by a proton transfer. So maybe I should write that down. So okay. And so when I use the phrase, X is the conjugate acid of Y, or Z is the conjugate base of A, there's always an acid and base in that sentence, okay? All right, and so the final thing I want to just talk about before we get into pKa's is what we call amphoteric compounds. And these are species that can behave as either an acid or a base. So okay, and again, best illustrated with an example. And so if we consider methanol, CH3OH, I can react that with a strong base such as amide anion, and that will deprotonate the methanol. So transfer a proton, push electrons in the OH bond down to oxygen. And what I end up with is the conjugate base of methanol, which we call methoxide, and the conjugate acid of the amide anion, which is ammonia, okay? But alternatively, for example, if you add HCl to methanol, you can actually protonate the methanol. So let me get a red arrow. And so I can transfer a proton to methanol. So in the first reaction, the methanol is behaving as a Bronsted acid. And in the second reaction, the methanol is behaving as a Bronsted base. And so in order to understand how a species is going to behave when it reacts with another reagent, you have to know quantitatively how acidic or basic it is. And that brings us into Ka's and pKa's and strengths of acids and bases. So let me move on to that here. Okay, so we're going to begin this discussion by drawing out an equilibrium. So we have HA plus H2O is an equilibrium with A minus plus H3O plus, okay? So what we're basically defining, or the reaction we're drawing, is the ionization of a generic acid, HA, in water. All right. And we can define an equilibrium constant for this reaction. And like all equilibrium constants, it's just going to be the concentrations of product over the concentration of starting material. So KEQ equals concentration of A minus times the concentration of H3O plus over concentration of HA times the concentration of water. Okay. Because water is solvent in this reaction, we assume that its concentration is invariant, so it doesn't change over the course of the reaction. And what we're going to do is multiply both sides of this equation by H2O. Okay, so we basically have H2O times KEQ equals A minus H3O plus over HA H2O and then times H2O. Okay, and then on the right side of this equation, you can see that the waters cancel out, and so we can simplify it and say concentration of A minus, concentration H3O plus divided by concentration HA. And this is defined as the what we call the Ka, or the acidity constant. Okay. And so the Ka gives me a sense for how much a given acid dissociates in water. And the values of Ka vary over many, many different orders of magnitude, depending on the species. And so to make it easier to talk about, we use a log scale. And so we would define the pKa as equal to minus the log Ka. So the two important relationships to remember are this one and this one. Okay. And so we're going to come back to this, but I'll say it now because it's a very important point. The lower the pKa value, the stronger the acid. So strong acids have low pKa values, and weak acids have higher pKas. Okay. All right, so let me go on then. Make sure I'm staying in the right order here. All right. And so the pKas allow us to rapidly determine the direction of an equilibrium when an acid and base are combined. So let me give you an example. So So the equilibrium is going to favor loss of a proton from the stronger acid. And as an example, let's consider hydrogen cyanide. So not a particularly, not one you want to be working with. This has a pKa of 9.4. Okay. And we can add methoxide. Okay. And so if I mix these two together, If I mix these two together, a proton transfer reaction can occur. If I want to draw that going sort of from left to right, I can start with a lone pair on oxygen, have that attack the proton on HCN, move the bonds, move the electrons in the hydrogen carbon bond to carbon. And what I end up with is methanol plus cyanide. Okay. And so the pK of methanol is about 15.1. All right. And so the equilibrium favors proton transfer from the stronger acid. And so we said that stronger acids have lower pKa values. And so the hydrogen cyanide is a stronger acid than methanol. And so the equilibrium favors the right. So okay. And we can actually get at the Ka or the KEQ for this reaction from the pKa's. So I can use pKa's to determine the value of KEQ. All right. And so remember that KEQ is simply, so let me, KEQ is simply concentration of products over concentration of reactants. And so I can make that expression here. So okay, so concentration of methanol times concentration of cyanide over the concentration of HCN times the concentration of methoxide. And so we want to get this back to pKa's. And so we're going to do a little bit of math here. We're going to multiply the right-hand side by concentration of water over concentration of water, or sorry, concentration of H3O plus over concentration of H3O plus. And so what I'm going to get then is, I will draw this on another board here. So KEQ equals methanol times cyanide times H3O plus over HCN times methoxide, times H3O plus. And then I'm going to rearrange this equation. And so what we're going to do is just rewrite it in the following form. So say KEQ equals CN minus times H3O plus over HCN. Okay. Times methanol over methoxide times H3O plus. Okay, and so what have I done? I've actually written out the expression for Ka of HCN. And on the right there, I've actually got the inverse of the Ka for methanol. So 1 over okay. And so then I can take it, keep going with this, and I can write then that KEQ equals Ka HCN over Ka methanol. Okay. And then remember that, draw this little side bit here, that pKa equals minus log Ka, and so minus pKa equals log Ka, and Ka then is 10 to the minus pKa. Okay, and so I can simply replace the Ka values with the pKa values. So I have 10 to the minus pKa of HCN over 10 to the minus pKa methanol. Okay, and that is going to be equal to 10 to the minus 9.4 over 10 to the minus 15.1. And if you do the math, then you get 10 to the 5.7. Okay. Okay. So this tells us then from the pKa's, we can determine that when you mix these two species together, the equilibrium constant is about 10 to the 6. So it greatly prefers the right-hand side of the equation here, okay? And that's consistent with the qualitative sort of descriptions that we gave. So we said that the equilibrium favors loss of a proton from the stronger acid. The stronger acids have a lower pKa value. And so the HCN has a lower pKa than methanol. So when you add HCN to methoxide, you get proton transfer to form methanol plus cyanide anion. So all this is just to illustrate how we can interconvert KEQs and pKa's and get a quantitative understanding of the extent of different acid-base reactions. All right. And so that wraps up lecture 5. I'm going to stop recording, and then we'll pick up with lecture 6.